Chapter 5, this is continuation from previous video, continuity equation. Okay, definition of continuity equation. Continuity equation comes from the conservation of energy. So what does the conservation of energy state? That matter cannot be created or destroyed. Okay, it is simply changed into a different form of matter. This principle is known as conservation of mass. Okay, we use it in the analysis of flowing fluids. Continuity equation is based on the principle of conservation of mass. Let's take a look at this figure. So we have control volume where there is a mass input and mass output. From here, we have mass flow in and mass flow out into the control volume. So for any control volume, the principle of conservation of mass says whatever in to the control volume must be equal to mass leaving unit time plus increase of mass in the volume per unit time. This is the principle of conservation of mass. But here, for a steady flow, there is no increase in the mass within the control volume. From this equation, if we have a steady flow system, okay, increase of mass in the volume will be 0. So there is no accumulation of mass in your system. Therefore, this equation becomes mass entering per control unit time equal to mass leaving per unit time. Okay, this equation becomes this. Okay, from the conservation of mass, it becomes mass entering per unit time equal to mass leaving per unit time with the conditions that we have steady flow for our system. Okay, this can be applied to a stream tube. This is figure for a stream tube. No fluid across the boundary. So in the in the stream tube, there will be no fluid that across this stream tube. So here there will be no fluid across this stream tube. Yeah. So how can we derive the Bernoulli's derive the continuity equation from this stream tube? So we know that mass entering per unit time at the N1 equal to mass leaving per unit time at N2. So we consider that the flow in this stream tube is steady flow. Okay, the fluid flow in this stream tube, this is stream tube, flows steadily. So when the flow is steady, what is the terms that will be equal to 0? In this equation, the terms that will be equal to 0 is increase of mass in the volume per unit time. Therefore, mass entering at N1 is equal to mass leaving per unit time at N2. Okay, so here we have mass entering per unit time, which means kilogram per second. So mass kilogram per unit time is per second. Therefore, here is mass flow rate at N1 is equivalent to mass flow rate at N2. So we know that previously in my video, I've already mentioned that the mass flow rate equation is equivalent to rho V A. So cross-sectional area, A is cross-sectional area. Therefore, we have to substitute this equation into this. Okay, so delta here means that there is a change of area for a stream tube. As we can see here, there will be a change of area size here for the N1 and N2. There will be a different size, okay, from these two N. Therefore, we wrote it down here because we deals with different area. So rho V delta A, cross-sectional area. So you have to substitute this equation into this equation. So for the mass flow rate at 1, so we change all these subscript for this all these unit, this equation into 1. So it will become rho 1 delta A1 U1. So U here is U average. Okay, here we have mass flow rate at 2. So we change rho 2 delta A2 U2. So this is constant. Why constant? Because steady flow, mass entering is equivalent to mass out. Okay, leaving string tube. This is the equation of continuity for the flow of compressible fluid. So for a compressible fluid, so what types of compressible fluid? For example, we have gas flow. That is compressible because gas can be compressed through a stream tube, U1 and U2. So from 1, U1 and 2, U2. Being a velocity is measured at right angles to the cross-sectional area, delta A1 and delta A2. So for the flow of a real fluid through a pipe or another conduit, the velocity will vary from wall to wall. However, using the mean velocity, the equation of continuity for steady flow can be written as, this is what I've mentioned before. In the fluid flow, for the fluid flow in the pipe, so we know that there is a no-slip condition phenomena. So no-slip condition phenomena will occur around the fluid, around the pipe inside diameter. So the fluid will stick at the wall, inner wall of pipe. So from here, from front view, we can see that the fluid will stick on this surface, okay, of the pipe. Therefore, it will affect to this to the velocity gradient in a pipe, and it will turn into parabolic manner. So the flow will be in a parabolic for a pipe. So you will learn this in the Hagen-Poiseuille equation. You will see that there is an equation to determine the parabolic equation for flow in a pipe. So from that equation, you can see that it is a parabolic equation. So in order for you to determine the velocity for a fluid in a pipe, we will use U bar, which is a velocity, mean velocity in a pipe. So that usually we will give you in the question mean velocity. So we will not give every layer's velocity, then you have every layers of the velocity. So we will not give this velocity for each of the layers. We will give you the mean velocity. And in the question, it will not mention about the average velocity. It will says or state that velocity of the flow that represent average velocity. Okay, from this equation, rho 1 delta A1 U1 equal to rho 2 delta A2 U2. We change velocity here to the average velocity. That's why this equation becomes rho 1 A1 U bar 1. So there is bar here, means that average velocity is equivalent to rho 2 A2 U bar 2. Okay, where A1 and A2 are the total cross-sectional area and mass flow rate of section 1 and section 2. So area 1 is cross-sectional area at 1 and area 2 is cross-sectional area at 2. Okay? So in fluid mechanics, we are dealing with incompressible fluid. So when it comes with these terms, incompressible fluid, we know that rho 1 for a fluid is equivalent to rho 2, equal to rho. Incompressible means that fluid cannot be compressed. So for example, the flow of water. Normally, incompressible fluid is for liquid. So incompressible flow means that the flow of liquid in the pipes. Okay. So for the incompressible fluid, incompressible flow, the density will be the same at point 1 and point 2. As we can see here, the point 1 and point 2, the density will be the same. There will be no change of density. The density will be constant. Therefore, rho 1 equal to rho 2 and equal to rho. From this equation, we can actually cancel out density. Because of the density is constant, rho divided by rho, and it will be cancelled out. These terms will become A1 U bar 1 equal to A2 U bar 2. As we can see here, this equation is actually equation of discharge. So we know that discharge Q is equal to A cross-sectional times with U bar. Okay, for point 1, cross-sectional area 1 times with U bar 1 is equal to Q1. Okay, so this equation can be write like this. Q1 equal to Q2. Okay, that is the equation for continuity equation. So the continuity equation, the mass flow rate in is equivalent to mass flow rate out, and because of the density is the same, and because of the density constant, or more precise is that fluid flow in the pipe is incompressible flow. Therefore, the density is constant. We can cancel out density. Then the equation becomes A1 U bar 1 equal to A2 U bar 2. So this is continuity equation. Okay, take a look at this example. We can apply the principle of continuity to pipes with cross-section which change along their length. So as we can see here, the cross-sectional area for both sections are different. So from section 1 to section 2, we can see that there are different size of area. So area 1 is much more bigger than area 2. At this point, we can apply the Bernoulli's equation in order for us to determine values for velocity, or we want to find the area, cross-sectional area at either section 1 or section 2. A liquid is flowing from left to right. So these arrows represent the flow of the fluid from left to right. And the pipe is narrowing in the same direction. By continuity principle, we know that A1 U1 rho 1 equal to A2 U2 rho 2, where this is the equation for mass flow rate. And the subscript 1 and 2 indicating the section 1 and section 2. From that equation, we know that the liquid flows in these pipes is incompressible liquid or incompressible fluid. Therefore, we can cancel out the term density because density is constant. So rho 1 is equivalent to rho 2. Then we can cancel out. Therefore, discharge at section 1 equal to discharge at section 2. Q1 equal to Q2. Then from discharge equation, we know that A1 U1 equal to A2 U2. So for example, from this equation, if the area A1 is 10 times 10 to the power of minus 3 meters square and A2 is 3 times 10 to the power of minus 3 meter square, and the upstream velocity. So the upstream velocity is the velocity at section 1. So this is upstream velocity and this is downstream velocity. Okay, you've been given the upstream velocity here, u1. Okay, in the example. So 2.1 meter per second. Then the downstream mean velocity can be calculated. So from here, we know that we already been given with A1, U1, and A2. But now the question asks us to find what is the velocity at point number 2. Or we can say that this question asks us to find what is the average velocity at point 2. So in order for you to get what is the average velocity at point 2, you have to rearrange this equation. Becomes, this is u2. Okay, u2 equal to a1 u1 over a2. Okay, and then you substitute all the values given in this equation. Then you get the u2 is 7 meter per second. So that is how we apply continuity equation in the question. Okay. So let's take a look at this example. This is nozzle where there is a different cross-section area for section 1 and section 2. So in this example, we are required to find the velocity entering the diffusion. So we are required to find what is the velocity entering the diffuser. So we know that from continuity equation, okay, mass flow rate at point 1 equal to mass flow rate at point 2. So from this equation, we know that rho 1 A1 U1 equal to rho 2 A2 and U2. So because of this fluid flows in this nozzle is incompressible fluid, therefore rho is constant. Rho 1 and rho 2 can be cancelled out. So we have A1 U1 equal to A2 U2. Okay, now we take a look at the question. Diameter 1 has been given 40 millimeter, and at section 2 diameter is 30 mm. So the mean velocity at section 2, so I wrote it down here. So diameter here has been given. So velocity here, this is what we are required to calculate, okay? So at section 2, the diameter is already been given, and same goes to area 2, not area 2, but velocity at point 2 already been given. Therefore, from this value, we need to substitute into this equation. So we know that to find the area at 1, at 1, we have to use by d squared over 4. If you want to use the equation for the area 1 by using the radius, it is okay, but you have to calculate it separately. So from this equation, area 2 also used by d squared over 4. So we have to differentiate between area 1 and area 2. So therefore, I put it d1 and d2. Okay, from that equation, we have to substitute into this equation. So you may calculate this value separately, or you can also substitute directly into this equation directly into this equation. Okay, so for me, I will directly substitute into this equation. So area 1 is by d1 square over 4. Okay, I times with average velocity at point 1 equal to A2 is pi d2 square over 4 times with u2. Okay, so rearrange this equation. U1 is equal to, so pi d2 square over 4 times with u2 divide by pi d1 square over 4. So from this equation, we can actually cancel out pi and 4 because when we rearrange, it will be cancelled out. Okay, therefore, this equation will become d2 square over d1 square times with u2. So you have to substitute the values for diameter 1 and 2 from this equation. So we substitute 0.3 divide by 0.4 square times with 3 meter per second. Okay, 3 meter per second. This is velocity at point 2. So we will get that velocity at point 1 is 1.69 meter per second. Okay, we already solved this example where the velocity at point 1 is 1.69 meter per second. So next, okay, what if we have one flow and divided to two flow? Okay, one flow here, take a look at this figure. We have flow at 1 and then separated into flow 2 and flow 3. So the total mass flow into the junction is equivalent to total mass flow out the junction. Okay, previously we know that the mass entering into the system, if we can draw a boundary here, so this is a closed this is a boundary. Whatever into the boundary is equivalent to and leaving the boundary. So here we have mass flow rate at 1 is equal to mass flow rate at 2 plus mass flow rate at 3. So we have mass flow rate at 1 is equal to, enter. Is there any arrows enter to this boundary? No, there is only 1. So mass flow rate at 1 equal to mass flow rate at 2 plus mass flow rate at 3. So from here, we change it into this equation. So rho 1, A1, U1 equal to rho 2, A2, U2 plus rho 3, A3, U3. So this equation, as you can see here, Q1 is A1, U1, Q2 is A2, U2, Q3 is A3, U3. This is simplified version from this equation. Okay, so the density is the same, constant. Density is constant, therefore we can cancel out the density terms in our equation. So rho 1, rho 2 and rho 3 can be cancelled out. So if the density is the same, what will happen to this equation? So it will be turns into rho 1 A1 U1 equal to rho, okay, A2 U2 plus A3 U3. So this velocity terms, I wrote it as rho. If rho 1 equal to rho 2 equal to rho. So I change it rho 1, rho 2 and rho 3 into rho. So rho and rho can be cancelled out. Therefore, it will left with A1 U1 equal to A2 U2 plus A3 U3, where we know that A1 U1 is Q1 here, A2 U2 is Q2, and A3 U3 is Q3. Okay, so let's take a look at this example. Okay, if the pipe 1 diameter is 50 mm, mean velocity 2 meter per second, pipe 2 diameter is 40 mm, takes 30% of total discharge, and pipe 3 diameter 60 mm. What are the values of discharge and mean velocity in each pipe? So from here, we know that we have to calculate what is the total discharge. From this figure, we know that velocity or discharge at point 1 represent a total discharge, because from 1 it will be separated into two pipes. Okay, from 1 divided into 2 pipes. Okay, so pipe 2 plus pipe 3 equivalent to pipe 1. So the amount of volume flow rate. So therefore, we have to calculate what is the volume flow rate or discharge at point 1. So let's calculate the discharge rate at point 1. So discharge is A1 times with U1. So therefore, A1 is pi d squared over 4. So pi d squared over 4. So this is diameter 1 times with velocity 1. So from here, when we substitute the value, we will get 0.00393 meter cube per second. This is the total discharge, because 1 is the total discharge for 2 plus 3. So we have 2 plus 3 is equal to 1. Therefore, this is total discharge. So here, the info in the question mentioned that pipe 2 diameter is 40 mm, takes 30% of total discharge. Therefore, we know that Q2 is 30% from total discharge. We know that Q1 is a total discharge. Therefore, we multiply 0.3 represent 30%, okay, times with 0.00393, you will get the value for Q2 is 0.001179 meter cube per second. Now we have flow rate 1 and flow rate 2. What about the flow rate 3? We know that from the continuity equation, Q1 equal to Q2 plus Q3. So from here, we can find what is discharge at 3. So rearrange the equation. We know that Q3 is Q1 minus Q2. So you have to minus Q1 with Q2. So you will get the value for the Q3 is 0.00275 meter cube per second. So in this question, in this example, also asks us to find what is the mean velocity in each pipe. So we know that the mean velocity of pipe 1 is already been given. And what about pipe 2? No. So we have to determine the mean velocity at point 2 and point 3. So we have to use the equations of Q2 equal to A2 U2. So we know that this U2 represents mean velocity. So rearrange this equation. So U2 equal to Q2 divided by A2. So before you calculate the A2, so you have to change mm into meter, because this is not SI unit, so you have to change millimeter into meter before you substitute into this equation. Therefore, from here you will get the value for U2 is 0.972 meter per second. Okay, so this is velocity at point 2. So Q2 is already calculated before here. So substitute the value, and then area is pi d squared over 4. And diameter must be, the unit for the diameter must be changed into meter before you substitute into pi d squared over 4. So what about Q3? So from Q3 we know that equation is Q3 equal to A3 times with U3. Rearrange this equation, you will get U3 equal to Q3 over A3. Again, substitute. To find area 3, you have to substitute with unit meters of diameter. So please do not plug in this value directly, because you have to change into SI unit. So 60 millimeter will be 60. For example, you want to change 40 mm. So you want to change into meter. So 40 times 10. Milli is minus 3. Millimeter is 10 to the power of minus 3. So you have to multiply with 10 minus 3 meter. So after you change into the unit of meters, then you can plug in your value into pi d squared over 4. So area is pi d squared over 4. So before you substitute diameter into this equation, you must make sure that your diameter is in meter. Okay? Same goes to 60 mm. So if we want to change mm to meter, 60 times milli is 10 to the power of minus 3 meter. Okay? Then after you change mm unit to m, therefore you can substitute into cross-sectional area. After you substitute into cross-sectional area, substitute into this equation to find what is U3. From here you get U3 is 0. This is not 0.972, it is 0.937. Okay, for U3 is 0.972 meter per second. So you already answered your question. That is how you use continuity equation in solving question that relates to the part. Okay, so that's all for continuity equation. Thank you.